We're going to do a related rate problem that is going to involve a cone. And a cone has a little bit of a trickiness to it that we got to work with. Almost every single cone has this problem, but let's kind of organize it and see. And we'll talk about where that problem is and how we get through it. So we have a water tank, has the shape of an inverted right circular cone with a radius of 15 meters at the top and 12 meters deep. Water is flowing into the tank at a rate of 2 cubic meters per minute. How fast is the depth of the water increasing at the instant when the depth is 8 meters? All right, so let's draw ourselves a picture. We need a cone, right? And it's an inverted. And so let's go here. We have a height to it. And we have a radius to it. All right, so we have waters filling it up. So at the beginning, it's going to fill up fast, but we're pouring it in probably at a specific kind of cubic volume per whatever. How about right here? So the flow is pretty consistent, but it's going to slow down because you're talking about more volume as you go up, right? So at every moment, the rate at which this height is changing is going to be different. So we're looking for a very particular one. So we are given, it says a water tank has this, the radius of 15 meters at the top. So 15 meters and 12 meters deep. So clearly my picture is not to scale. Water is flowing into the tank at a rate. So we are given the rate at which the volume is changing is 2 cubic meters per minute. All right, and we're pouring water in, so our volume is increasing, so we'll leave it as a positive. And we are trying to find how fast is the depth of the water, so find the dH/dt of the water increasing at the instant when the depth is, so when your height equals 8 meters, right? So it's 12 meters, so we're kind of up towards the top, a certain fraction of the way up. All right, so if we are looking for all this information, we need some sort of a formula, and we are talking about a cone. So the volume of a cone is 1/3 pi r squared h, right? That's what we got going on. And we would be doing the derivative of this with respect to time in order to create these dv dt's, dh dt's, right? But we're not, because the problem is going to be that when we do this, we are going to be creating a dr dt and a dh dt because we have a product rule between them. And so we'd be taking the derivative of each of those variables with respect to time and creating that. The problem is that we don't know what the rate at which the radius is changing, and we're not going to find it. So we have to basically get rid of an r. We need to sub out an r and replace it with an h. Okay, that's what we pretty much always have to do on these types of problems with cones. So here's where, let's just take this triangle in particular. So we're looking at this triangle is 15 and 12, right? That's what we got. So we actually have a proportion. We have the 15 and a 12 is the proportion of the radius compared to the height. So it always has that kind of a ratio, no matter where you're at. If you're here, we have a radius and we have a height, but it still has this same proportion, which is huge because let's cross multiply. And we would get a 12r equals a 15h. And since we're trying to find stuff related to h, we don't want an r in our equation. So we want to sub that r out. This is exactly what we need in order to do that. We are going to divide the 12 over and get this in terms of h. So we're going to isolate the r. So 15/12, we're going to cut out a 3 out of those, so 5/4. So 5/4 h. All right, so I can take that value and replace our r with 5/4 h. So let's do a little math real quick here, and then we'll come back to doing the derivative. So we're going to take our 5/4 h, square it, multiply it by h. Now we won't have an r in that equation, which means we also won't have a dr dt. Perfect. So this is going to be 25, so pi over 3, sorry, 1/3 pi times 25/4, 16ths, let's call it, 16ths. And then that's h squared combined with that h is going to be h cubed. If I put that together, our volume is 25 over 48 pi h cubed. All right, now we're ready to take our derivative with respect to time. So that'll give us a dv dt equaling, if I bring the 3 in front, that's going to make that a 75/48 pi h squared dh dt, because of the chain rule, doing the derivative with respect to time. And then I can see what we have, what we're plugging in, what we're looking for. We have a dv dt is 2. So 2 equals 75. I can simplify that. And here's why I know. I had a 3 here, a third in the denominator, 3 in the denominator, and then I brought a 3. So I know that I can simplify a 3 out of both of those two. And so I kind of cheat this, that if I divide that by 3, that's going to get me back to 25. And I divide that by 3. I used a 3 and a 16 to make the 48. So that'll bring that back to 16. So I'm looking at a 25/16 pi. H, we have a very particular moment. We want 8 squared. And the only piece we don't know is dh dt, because that's what we're looking for. All right, let's keep fighting through the math here. So we have a 2 equals. Now I'm going to organize this because I'm going to try to do this whole thing without a calculator and see what we can get. So I'm going to start to really kind of make our fractions here. So we have a 25, a pi, and a 64 over 16 times dh dt. So I would be dividing that over, which means I'm also multiplying the reciprocal over. So I would have a reciprocal of 25 pi 64 multiplied together times 2 over 1 would equal my dh dt. Okay, so instead of dividing that over, I'm multiplying the reciprocal over. So I'm going to leave them all in these individual pieces. I'm not going to multiply stuff because then I can simplify a little nicer. So I can take, I think I can take 16 out of that, but I know I can take an 8 out of that. So I can get an 8 and a 2. Then I can get a 4 and a 1. I can get a 1 and a 2. All right, a lot of these are set up to be pretty clean in the end. So my fraction here is I don't have anything left except for a 1 on the top. I have a 25 pi and a 2. So a 50 pi is my dh dt. So let's organize this. So our change in our height with respect to time at this instantaneous moment when the height is 8, the change in the height is 1 over 50 pi, and it is in meters per minute. And that is our rate at which the height is changing.